Continuity and one-sided limits. The informal definition of continuity that you're able to draw the whole graph without ever lifting up your pen or pencil. The technical definition of continuity is that for it to be continuous at a point, it needs to be defined there. So f of c needs to actually exist and be a number. Your limit as you approach c from each side has to exist. And the third one saying the first two have to be equal to each other. If it fails any one of these three parts of the definition of continuity, then we would consider it to be discontinuous at x equals c. Now, there are different types of continuities. The one on the left and the one on the right are basically holes in your graph. A hole is referred to as a removable discontinuity because you could actually define a new function to actually cover that hole. Then we have a finite jump. That would be like the center graph up here, where you're going along and all of a sudden your graph jumps up or down from one point to another point. And then there's infinite discontinuities, and that's what happens when you have a vertical asymptote. And that does not happen to be shown on this slide. So let's go ahead and talk about the continuity of each one of these four functions. The first one, 1 over x. Well, you know when you're dealing with 1 over x, you can't divide by 0, so you know you'd have a problem at x equals 0. You should know from looking at this prior in your past classes that 1 over x would have a vertical asymptote at 1 over 0, or at x equals 0. Now, you'd have a vertical asymptote. Your limit on the right would go towards positive infinity. Your limit on the left would go towards positive infinity, or negative infinity, so it would not pass the second test. Doesn't pass the first part of the definition either because it's not defined at x equals 0. Now when you look at the second one here, the second one does factor. It factors into an x plus 1 and an x minus 1 all over your x minus 1. So g is going to go ahead and do some simplifying down. It'll simplify down to an x plus 1 except when x is equal to 1. So it's going to be continuous at all functions or places except at x equals 1. At x equals 1, since we could remove that factor that was giving us a problem, it's referred to as a removable discontinuity. It's a hole. C, when we look over here, h of x is a piecewise function. Now, here we just have a line, here we just have a parabola. We know lines and parabolas are always continuous. So the question is, where might we have a problem? Well, that would be if these two here are going to meet up or not. And that would be when x is equal to 0. Well, the first definition of continuity says that it needs to actually be defined there. Well, does h of 0 actually exist? Well, when you take 0 and it says equal to x here, you could plug it in here and you get 1. So yes, it does exist. The second part says, well, your limit has to exist. Well, we're wondering about our limit as x approaches 0. Well, it's not just one function, so we got to look at our one-sided limits. As you look at x approaches 1 from the right, that's number slightly greater than 0. That would be this one here. So as you're approaching from the right-hand side of 0, you take something you're really close to 0 and plug it in, you essentially get 1. Looking at your left-handed limit, looking at numbers slightly less than 0, you'd have to plug it into the top one because that's what it's defined for. And you plug it in and you get 0. Since your left-handed limit equals your right-handed limit, and that's 1, and that's the same as what it's defined to be, well, then it's going to be continuous. Over here on the far right, we have our sine function. You should remember a sine. You can draw your graph without ever lifting up your pencil with your sine. There's no questionable marks on it, so it's continuous at all real numbers. As you look here, we really have the graphs of all those that we were just talking about. Here's your vertical asymptotes. Here's your hole we talked about. Here's your parabola coming into your line. Here's your sine function. Now, once again, we've talked informally about one-sided limits. If you have a little plus as an exponent, that means you're coming in from the right-hand side. You're choosing numbers slightly greater than a. If you have a little minus as an exponent on your a, that means you're coming in from the left and you're choosing numbers slightly smaller than a. So here we have an example of some limits. We're wondering about our limits as x approaches 0. We have our absolute value of x over x and plus 2. So if we look at the graph over here of numbers slightly larger than 0, that would be coming in from this way here, slightly larger than 0, and we're leveling out at a height of 3. Here this is saying, as you come in from the left side, slightly less than 0. So we come in from this way here, and we're always at a height of 1, so your limit there is 1. Now, your two-sided limit is only going to exist if these two numbers that you just figured out from your one-sided limit are equal. Since 3 does not equal 1, we would say your two-sided limit does not exist. But we do have one-sided limits that exist. Now, when you're working with one-sided limits, it's basically saying up here in the top, just go ahead and plug it in to figure out your limit. If that works, great. But to check for your continuity, you want to know, is it defined there? And is what it's defined there to be equal to your limit? So it's really going through the three parts of the definition of continuity. Continuity here says if f and g are continuous functions and you add two continuous functions together, it's going to be continuous. If you multiply two continuous functions together, it's going to be continuous. If you divide two continuous functions together, it's going to be continuous except wherever the bottom function is 0. Now, down below it's saying all polynomials are continuous. All rational functions are continuous except where it's undefined because you're dividing by 0. Radicals are continuous, assuming you don't have a negative underneath an even root. And your trig functions are continuous except where you have vertical asymptotes.